So welcome to today's topic, which is how does a safety instrumented function achieve its SIL? So what is a safety instrumented function? The standard defines it as a single set of equipment designed to deal with a specific single hazard to automatically bring the system to a safe state. So for example, if we had a scenario that could generate a high temperature, high pressure, and a high level, we would have three different SIFs. We would have a SIF to deal specifically with the high pressure. We would have one to specifically deal with the high temperature and one to specifically deal with the high level. And the safety instrumented function, as the name implies, is going to consist of combinations of sensor or sensors, logic solver, and final elements. And this is different from the safety instrumented system. And oftentimes when I talk to clients, I get a feel for how well they understand what the difference is, because sometimes they'll say to me, well, it's a SIL2 system. Now, this is incorrect and ambiguous because the safety instrumented system does not have the SIL assigned. The SIL, the safety integrity level, is assigned to the safety instrumented function. And the reason is because, of course, as I just mentioned, you can have different SIFs to deal with different scenarios, and they can have different safety integrity levels. And remember, the safety integrity level is to indicate how much risk reduction we expect the safety instrumented function to provide us. And there are four levels. There's SIL1, SIL2, SIL3, and SIL4. So the risk reduction provided by a SIL1 would be between 11 and 100. The risk reduction provided by a SIL2 would be 101 up to 1,000. A SIL3 would be 1,001 to 10,000, and a SIL4 is 10,001 to 100,000. Now, typically in the process industries, we are dealing with SIL1 and SIL2 and occasionally SIL3. We never get to SIL4. SIL4 is mostly for the nuclear industry with some railway signaling. We've seen SIL4. But typically we're dealing with SIL1, SIL2, and occasionally SIL3. So it's very important that we understand that difference because the safety instrumented system can act in multiple ways to prevent multiple harmful outcomes, which can consist of one or more SIFs with different SIL requirements. So it's the SIF that always has the SIL assigned. So if we consider this, here again, people often say to me, if I've got a SIL2 sensor, a SIL2 logic solver, and a SIL2 final element, I must have a SIL2 SIF. No, not necessarily, because the SIF will consist of not just the sensor, but any conditioning. So if we have, for example, IS requirements, intrinsically safe requirements, we might have IS barriers. We might have interposing relays because of different voltages. We may have splitters and so on. So those have to be considered as well. And then for the logic solver and the equipment in general, there's the power supplies. We might have instrument air. There are interconnections. All of that has to be considered. And here again, on the final element side, we might have solenoids, actuators, positioners, etc. So all of those have to be taken into consideration along with the final element. So it's basically tip to tail and everything in between. So this is very important to remember. So when we're looking at the SIF, that is what we're looking at. And the other thing about safety instrumented functions is that they are independent protection layers. And when we come to look at independent protection layers, there are four things that we have to consider to qualify as an independent protection layer. Firstly, it must be specifically designed to be capable of preventing the consequences. Hence the example I gave you with the SIF to deal with the high pressure, the SIF to deal with the high temperature, and so on. They must be completely independent from all other protection layers. And this one often gets violated We've seen it many times where we're trying to share a final element between the BPCS and the SIS. And then thirdly, the dependability. This is very important because the dependability requires that we must be able to act dependably when the hazard occurs. And so therefore we have to have sufficient defense against systematic and random faults. And some of you who may have been on previous webinars of mine know that I characterize systematic as being the 3 Ps. So first and foremost, are the people properly trained and competent to do the work? Do we have clearly written procedures and processes that are being followed? And thirdly, do we have paper trail to prove that we're doing what we said we were going to do? And then the random faults also we have to have defense against random faults. So this is very important, and this is part of our SIL verification process that we go through. And then finally, we have to be able to test and maintain it to ensure that the risk reduction is continually achieved. So this is also a very important part. So when it comes to looking at the safety instrumented function and achieving the required safety integrity level, there are 3 things that we have to consider. And here again, oftentimes people say to me, well, I met the PFDavg, so I'm good. I don't need to do anything else. No, that's one of 3 things. So this isn't a 1 out of 3, it isn't a 2 out of 3, it's a 3 out of 3. We have to meet all 3 of these in order to achieve the SIL. So the first thing is, do we have sufficient defense against the random failures? And random failures are used in our calculations of the PFDavg and the PFH. So this is to meet the D in SIDA for random failures. Do we have sufficient defense against random failures? The second one is the architectural constraints. In other words, what is the minimum hardware fault tolerance that we need to achieve the SIL? And as we shall see, there are 2 routes we can take with this. We can either follow the 1508 route 1H, or we can follow the 1508 route 2H, or we can follow 1511. So in the 1511 standard, it gives us the option to use the tables in 1508 or the table in 1511, which I will talk about in a moment. And then thirdly, the SIL based upon the systematic capability. This, of course, is also important because this is how we meet the D in SIDA for systematic failures. So like I said, we have to meet all 3. And we will be limited to the lowest SIL achieved. So for example, if our target was we needed a SIL 2 SIF, our systematic capability was SIL 3, the hardware fault tolerance met SIL 2, but our PFDavg only met SIL 1, then we would be limited to SIL 1 and we wouldn't meet our target of SIL 2. So like I said, we have to meet all 3 in order to achieve the target SIL. So the purpose, as I've said, of the first requirement, meeting either the PFH or the PFDavg, is for the defense against random failures. So do we have sufficient defense against random hardware failures? And of course, the level of defense varies by an order of magnitude per SIL level, as we've said. So the amount of risk reduction will be determined by the SIL level we can achieve and the corresponding risk reduction. The other thing to bear in mind is when we're doing calculations, we need to use failure rates that are credible, traceable, documented, and justified. The 2016 edition of 1511 has this clause 1193 included. And this just reinforces what reliability engineers have long understood, which is that we need credible failure rate data. Part of the problem, and maybe part of the reason why this was put in 2016, is that some manufacturers were publishing failure rates which were not credible. Now, fortunately, there are plenty of sources of finding failure rate data. And we have provided a website called SIL safe data, all one word, .com, where you can look at different types of devices and it will give you a lower bound DU failure rate and an upper bound DU failure rate, dangerous undetected failures. Because if we're using failure rates that are too optimistic, you will end up with overstating the amount of risk reduction that the SIF is going to provide. So you'll get unrealistically high values, which you don't want. You want to have realistic, and that's why this clause is in there. So the failure rate data that we use has to meet this. The other thing to remember is, and there's another webinar that I did on this about useful life. For safety instrumented systems, we cannot have a run to fail. We have to follow the useful life. And that's because during useful life, we are justified in claiming a constant failure rate. Once we get outside of useful life, the constant failure rate doesn't hold true. So our calculations will not hold true. And again, we can start off with having everything right, but if we're not going to follow through with the requirements for the auditable side, I should say, which is, can we test it and maintain it, then we're going to have a problem. So this is very important to understand, and we still have some people asking us to use failure rates that they've gathered which are not credible, and we can't use them. So when it comes to doing this, there are 9 key variables you have to consider. First and foremost, as I've just mentioned, is the failure rates of each product, including failure modes and any diagnostic coverage. So depending upon the device, if it's intelligent and it has diagnostics, we can make use of that. And of course, this is going to be an attribute of the actual product itself. Mission time. So here again, when I teach the FSC 100 class, I always tell any designers in the class that you cannot design in isolation. You have to be talking to the end user, because the mission time, this is the time that we expect a set of equipment, SIF equipment, to operate before either overhaul or refurbishment, replacement. And again, this will be an attribute of the end user practices, what they're used to doing. So this would be defined by the end user. The proof test intervals are also going to be assigned by the end user practices, depending upon the size of the plant, the size of the system, the number of SIFs, the number of personnel they have. There could be restrictions on what they can do. And for example, we were approached by a client because the engineering company, in order to meet the SIL target, had set the proof test intervals at 3 months. And the client said, there's absolutely no way we are able to do this every 3 months. So we worked with them and they said they could handle a year. We had to change the mission time. Now, there's another webinar I did on this where the mission time, proof test intervals, and proof test coverage or effectiveness plays into the PFD average. So you might be interested in looking at that if you haven't seen that one. So proof test intervals, again, defined by the end user. The effectiveness is going to be an attribute of the proof test method. And here again, you can design a proof test that can be very efficient in terms of coverage, giving you high coverage, but if it takes 8 or 9 hours to perform, well, guess what? It's not going to get done. So the effectiveness is also going to be defined by the end user. The proof test duration, how long does it take to do the proof test to itself. As I've said, that's an attribute of end user practices. So here again, the availability of the manpower to do it, having proof test procedures that are efficient and optimal and not going to be too long. This will be defined by the end users again. The mean time to restore. So the time it takes to detect the failure, fix the failure, and restore the SIF to normal operation will also be defined by the end user practices. So here again, the mean time to restore is a variable that is defined in the SRS, and it needs to be done not independently by the engineering company, but it needs to be done in collaboration with the end user. Because again, how long it takes them to do it, that's going to be an end user. And the probability of the initial failure. Here again, as I've said, day one, everything could be fine, but if we're not following through, if the end user is not following through with doing the testing, following mechanical integrity, doing the repairs properly, tracking useful life and so on, then the probability of the initial failure is going to be higher. And that is going to be affected by the end user. The redundancy of the devices, including any common cause failure, is an attribute of the SIF itself, which is part of the system design. And then finally, this one is very important, the operational maintenance capability. This basically comes down to the site culture. How good is our site safety culture? In other words, are we tracking the proof testing? Are we doing it according to the SRS? Are we doing the mean time to restore according to what's defined in the SRS and so on? If not, then of course we're going to have problems. And so this is also down to the end user. So you can see out of these 9 variables, 7 are directly impacted by end user practices. So designers cannot design in isolation. They have to be talking to the end user, operation and maintenance people, find out what are the sore thumbs when it comes to doing maintenance so that we can avoid that. Don't set unrealistic proof test procedures that are 60, 70 pages long, because again, they will be probably truncated and not done according to the requirement. So predominantly in the process industry, we talk about low demand. This is where the SIF will be sitting there for potentially years, not being called into operation. And of course, that's where the following through with the maintenance requirements is very important. So we use PFDavg in low demand modes for long periods of time. And then of course, if we have any high or continuous demand mode applications, machine safety, for example, we need to look at a different metric, which is the probability of failing per hour. And both of those will be based on random failure rates. So we're back to clause 11.9.3 again. Are we using credible failure rate data? And you can do the calculations manually with spreadsheets. Well, good luck with that, because some of these variables are not easily put into a spreadsheet. You can use generic fault-free tools and purpose-made SIF verification tools. Here again, the standard now requires us to qualify the tools. How do we know that the tool is generating the right answers? Or as I like to say, it could be garbage in, gospel out. You're believing what the tool's telling you, even though it's been fed a load of rubbish. And we know, as I said, that the Excellencia tool, we've had that evaluated independently up to SIL 3. So we know we're good for SIL 3. We're probably good for SIL 4, but we haven't had it evaluated to that. And if any of you have used Excellencia, then you're probably familiar with the silver tool, as we call it, the SIL verification tool. So here we can represent our SIF with a simple block diagram. And you can see here that we have a single pressure measurement, pressure transmitter of some description. We have a generic SIL 3 logic solver. and we're using 2 valves in a 1 out of 2. Now, embedded in Excellencia is failure rate database for most of the manufacturer's devices. But if there's a device that you can't find, we have generic devices. Now, generic devices provide slightly more conservative failure rate numbers. So if you meet your target using generic devices, then you're going to meet the target using actual devices. And you can see at the top here, we have a requirement for a SIL1 with a risk reduction factor of 22, and we've achieved a SIL1 with a risk reduction factor of 42 with this particular design. And then it shows you what is the contribution to the PFDavg and the corresponding mean time to fail safe. And you can see that for each of the sensor, the logic solver, the final element, and then the SIF overall and what it achieved. So the SIL, the PFDavg SIL was 1. For the sensor, the architectural will be 1. The logic solver, SIL 3. The final element meets SIL 2. And the systematic capability is not being assessed because we're using a generic device. Once we figure out which logic solver we want to use, then we need to consider the systematic. Because remember, the systematic is one of the 3 things that we have to meet. And if you choose not to consider systematic, you've got to have a very good reason why, and you have to document that. You can also see the response time here in milliseconds. So this particular design has a 6-second response time, and you can see the contribution to the PFDavg. Because we've got 2 valves now, it's not the final element, it's the single sensor. But you can see, because we've got 2 valves in a 1 out of 2, the final element is the major contributor to the mean time to fail safe. So these charts can be these pie charts can be useful if you're missing your target, because you can see where you need to concentrate. And then further down here, you can see that the architectural constraints are using the 1508 tables. Remember, 1511 allows us to use 1508, or that we can use the 1511 table, which I'll talk about in a minute. In this case, our mission time is 15 years, and we're in low demand. And the site safety index is the capability of the site. So normally we default to good, give people the benefit of the doubt for the sensors, the logic solver, final elements. But if you're struggling with final elements, for example, where you're not able to meet your mean time to restore target, then you can adjust that down because it'll alter the overall PFD average. So that's an example of a SIF verification tool. So having met barrier number 1, how do we meet barrier number 2? And as I said, the purpose of barrier number 2 is to impose minimum hardware redundancy requirements, which can either be met from one of the 3 charts in 1508 or the chart in 1511. And architectural constraint applies to each element separately. And an element is commonly defined as a subsystem. So sensor would be an element. The purpose of meeting this requirement is to protect against any unrealistic parameter estimates in the PFDavg or PFH calculation. Remember, we have those 9 variables that we need to be able to meet. So what are the tables? In the 2000 edition of 1508, when it first came out, it used root 1H, where it defines 2 types of devices, a type A device and a type B device. General rule of thumb is a type B device will be any device that has any embedded firmware or needs programming of any description. Type A will be simple analogs, actuators, valves, for example. Those would be type A. And under root 1H, it used something called the safe failure fraction. So very simply, the safe failure fraction was a ratio of the safe failures, which is the safe detected failures, the safe undetected failures, and of course, the dangerous detected. Because if we can detect dangerous failures, they're no longer dangerous. So they move to the safe side. So that would be the ratio of the safe and dangerous detected failures over the total. And that would be between, as a fraction, 0 to 1. So the higher the safe failure fraction, the more inherently fail-safe the device is. And the way you use the table is if we have a safe failure fraction of a type A between 60 to 89% with a hardware fault tolerance of 0, then we can use that for a SIL2 application. For a type B, on the other hand, if it's between 60 and 89% with a hardware fault tolerance of 0, we can only achieve a SIL1. So these are the tables based on type A and type B with a safe failure fraction. In the 2010 edition of 1508, it introduced root 2H, which basically says you can reduce your hardware fault tolerance by 1 if the accuracy in the field failure data is 90% or better. And if a device is tagged as 2H, then we can use the 2H table. And as you can see, there's no safe failure fraction. It basically says with a hardware fault tolerance of 0, you can get up to SIL2. If you want SIL3, you need at least 1 level of hardware fault tolerance. So this is in 1508. In 1511, it just has one table now. The old 2003 edition of 1511 had 2 tables. It had a logic solver table with safe failure fraction, and it had a field table. What they've done now in 2016 is done away with that, and we just have this one table. And you can see for a SIL1 in any mode being low demand, high demand, or continuous, hardware fault tolerance of 0. For SIL2 in low demand mode only, hardware fault tolerance of 0. And if it's high demand or continuous, you need 1 level of hardware fault tolerance. And SIL3 would be 1 level of hardware fault tolerance in any mode. So in low demand, this ties up with the 2H table. So 1511 allows us to use this table, or we can use the tables in 1508. So that's for barrier number 2. What about barrier number 3, the systematic capability? So as I said to you, the purpose of this is to show that we have sufficient defense against those systematic failures, the D in SIDA for the systematic. And 1511 requires us to justify the equipment selection by 2 means only. Either the use of 1508 certified devices, or we have to do prior use. Those are the only 2 methods of justification. And I always tell the designers the easiest method is to use 1508 certified devices, because it's an easy way to document and demonstrate compliance with 1508 as required by 1511. It should be done by an accredited, technically competent and well-known third-party company, although manufacturers can self-certify if they choose. And a good certification assessment will demonstrate that there's high design quality for the hardware, the software, and the manufacturing. And it will also check to make sure that the proper end user documentation is provided. In other words, the safety manual. So you can see on this certificate, if we look here, we have a systematic capability of SIL3, which means we can use it in a SIL1, a SIL2, or a SIL3 design. It is a type B element, and in order to do SIL3, we have to have a hardware fault tolerance of 1 following root 1H. So you can see that's specified on the certificate, and this is the easiest way to go. If not, we have to follow prior use. And the purpose of prior use is, number 1, to demonstrate the SIL capability of a device based on previous operating experience in similar operating profiles. So in other words, are we comparing apples to apples? It doesn't necessarily have to be in a safety application as long as the operating conditions and environment are the same and that the process is the same. But the most important point is that we need to gather evidence that the dangerous systematic faults have been reduced to a sufficiently low level compared to the required safety integrity. Now, this is where the crux of the thing comes in, because if you haven't been properly recording failures and doing the relevant root cause analysis, in other words, when something fails, did it fail safe or did it fail dangerously? If it failed dangerously, was it because of a systematic issue or was it because of a random issue? So if we don't have that information, it's very difficult to meet this requirement. And if the end user doesn't have the information, you have to go back to the manufacturer. And unless you're a big user of their device, they might not be too willing to help, at least unless you pay them. So we've helped companies do prior use justification, and it's not necessarily straightforward and easy, and it can be time consuming. So this has to be done in addition to making sure we meet the random requirement. Remember, we still have to meet the random failure rate requirement. So we would have to do a calculation on that or get the information from the manufacturer. So even though they list quite a few of the items that need to be included, they don't really give too many details on what's sufficient. So for example, 1511 lists 4 key items that have to be investigated for prior use. Firstly, consideration of the manufacturer's quality management and configuration management system. So there's that nice open-ended word, consideration. What does that mean? Adequate identification and specification of components or subsystems. Here again, adequate. What does that mean? Demonstration of the performance of components or subsystems in similar operating profiles and physical environments, as we mentioned. And then it talks about the volume of the operating experience. What do we mean by the volume? So here again, those specifics regarding the extent of the manufacturer's quality audit, the level of documentation, detail of identification requirements, and the volume, of course, are not stated. We provide some guidance on this when we talk to clients about doing prior use. And if you use Excellencia, Excellencia actually has a prior use checklist that can help with justification. So let's sum this up then. In order to meet the SIL, a SIF has to meet all 3 requirements: the defense against random failures, which is the PFDavg or the PFH, the architectural constraints in terms of the required hardware fault tolerance, and the other D, consider the other part of that D, dependable, is the systematic capability. Do we have sufficient defense against systematic issues? So we have to meet all 3 of those. And there are 9 key variables that have to be considered for meeting the PFDavg, as we discussed. Designers need to use 1508 certified devices wherever possible to meet the systematic capability. And there might be instances where we can't find a certified device, in which case then we still have to do the prior use justification. So as I've said, wherever possible, we need to use the certified devices. We have to justify the equipment, as I've said, and there's only 2 routes, the 1508 route or the prior use justification. And any failure rate data that's used in the calculation must meet that clause 1193. In other words, the failure rate data has to be credible, traceable, documented, and justified. Any equipment used in a SIF must be within useful life. Otherwise, the calculations don't hold true. This is something that a lot of people are not tracking. And it is very important because when it comes to functional safety and probability, it's all predicated on constant failure rate during useful life. And you can use the purpose-made tools such as Excellencia as long as they're qualified for use. So these are the key things to remember. Just about me, now I'll do the introductions. So I've been in the industry now 48 years. I started off developing safety systems and then moved into more of a corporate role, and then the last 13 years since I've been with Exida, I've been primarily focused on the functional safety realm, and I'm one of the primary instructors for the functional safety class. A little bit about Exida, if you don't know. The company's now 25 years old. It was founded by two original founders. One was the client, one was the vendor. The client was Bill Goebel from, at the time he was with More Products, wanting to get his system certified to this new standard that had come out, which was 1508. And Rainer Fuller, who was at the time working with TÜV Rheinland. And as Bill likes to say, of course, he crashed and burned when it came to meeting 1508. And he said to Rainer, what do we need to do to fix it? And they said, well, we don't do that. So they sort of had an aha moment and decided, well, the other manufacturers are going to be in the same boat. So that's how Exida started. And Exida stands for Excellence in Dependable Automation. And we started off doing basically certification for functional safety for products. We've grown exponentially since then. We now have full lifecycle services for alarm management, cybersecurity, functional safety, along with all the relevant training. We also do certification for people, the CFSE, CFSP, CACE, and CACS on the cyber, and we do product certification for cybersecurity now. Along with that, we have our tools, which is part of our development team, deal with tools and created the Excellencia Lifecycle tool. We're global. We're in most countries around the world now. And the nice thing about the three, the cybersecurity, functional safety, and the alarm management, is what we like to call industry agnostic. You can apply it to any industry that requires it. So we've worked in mining, steel, utilities, oil and gas, chemical, LNG, mining, etc. So there should be some close to you if you need support. Reference materials, there's a lot of free information on the website. These webinars are also readily available as YouTube videos. This will be also put on the website afterwards as a YouTube video, and you can access those at your leisure. They're free. There's the SAEL, which is the Safe Automation Equipment List. So if you're looking for certified devices, that's the best place to go. And you can see which devices are certified and get a copy of the certificate. We also publish a lot of books. The manager's book was the last one that I did 5 years ago now. So those are available. And we also have published papers and case studies and things. They're all free. So I always encourage people to make use of the website wherever possible. The Excellencia suite provides a full lifecycle tool. So once you get the data into any one of these tools, it's available to the rest. And it flows from the hazard and risk assessment all the way through to the data gathering in the field, SIL stack. If we've identified alarms as layers of protection in the PHO or LOPA, those can be brought into the SIL alarm tool, so we can start to create a master alarm database. If you would like to know more, please feel free to reach out. So thanks for listening. And just one final note is we are holding a free one-day seminar in Houston on the 12th of September, which is Friday week. I myself and two other colleagues will be presenting. There's still a few spaces left if you're interested in the area and you can make it, but feel free. Bye for now.